So today we're going to talk about logarithmic equations. So this is still part of section 4.5, but it's a very different part of 4.5, and that now our equations have logarithms in them. So this is a very big transition, which is why I've given this title its own Roman numeral, okay? So this is a big change. We're still solving the equations, but they have logarithms in them. The rest of this section was exponential equations. These are logarithmic equations. There's two very distinguished types of logarithmic equations. Type 1, every single term is a logarithm. A logarithm minus a logarithm equals a logarithm. Every term is a logarithm. Type 2, not every term is a logarithm. In other words, a logarithm, oh, not a logarithm. So when you get an equation, a logarithmic equation, you want to first identify, is every term a logarithm or not? Because you solve them differently according to whether every term is a logarithm. All right. So in this section, there is a property here that says that when you have two logarithms equal to each other, something like if you have log base 4 of A equaling log base 4 of B. If the bases are the same and you have one logarithm equal to one logarithm, then you can set the arguments equal to each other. And we use this property when every term in the equation is a logarithmic term. All right? So let's take a look at it. So for instance, number 1, we want to solve it. Remember, when you solve, your answer is x equaling something. Okay, this has one logarithm equal to one logarithm. So I apply the property now that says you can set these arguments equal to each other. That's simple. If it's one logarithm equal to one logarithm, you can set the arguments equal. Now, true, the bases have to be the same. That's like a critical thing, but in general, they will be in each equation. So now this becomes easy to solve. It's just a linear equation. Subtract 2x from each side. Add 1 to each side, and divide by 3. There's your solution. So if a one logarithm equals one logarithm, then you can set the arguments equal to each other to solve. Part 2, number 2 here is exactly the same. This one, though, has a log base 10. It's a common logarithm. Both of them have the same base. It is a logarithm equal to a logarithm. So our property tells us that we can set the arguments equal to each other. And then solve. I like to move the x to the left side. So if I add x to each side, it would be 2x minus 7 equaling 5. Then if I were to add 7 to each side, it would be 2x equal to 12. And then divide by 2. Oddly enough, the answer is again 6, which would not always happen, of course. But there's another solving with that same pattern of a logarithm equal to a logarithm. Yep. Okay, so now this is not good. It's at the bottom of my page. So when I scroll up, I'm going to have to rewrite this question.
Just wait.
Choke on the next one. Okay, so I believe this is number 3. And it's supposed to say it because it was on the other page, but it should be log base 3. No, just log, right? Log of 3x minus 4 minus log of x plus 1 equals log of 2. Okay, so the minute you get a logarithmic equation, you immediately look and say, is every term a logarithm? Every term is a logarithm. Okay, so now I want one logarithm equal to one logarithm. Well, the left side, remember, with your properties, you can collect this together so that it will say log of the fraction 3x minus 4 over x plus 1 equaling log of 2. So you need to make it so you have one logarithm equal to one logarithm. Now we're in the same position we were in examples 1 and 2, so that I can set the two arguments equal to each other. Now when you have a fraction involved, this is where we would want to come in here and cross multiply. So I would cross multiply, make this like a 2 over 1. So I'd have 2 times x plus 1 equaling 1 times 3x minus 4. Again, a very simple linear equation. This becomes 2x plus 2 equaling 3x minus 4. Now if I move my variable to the left, I would subtract 3x, which would make this a negative x plus 2 equaling a negative 4. Then I would subtract 2 and get negative x equal negative 6. I don't know what the deal is, why every one of these examples has this answer. This is not going to be consistent, okay? This is most unusual. I don't know how this happened. Don't memorize the answer is 6, okay? That's not a good thing to do. Okay. All right, so the next one, which was on the page prior, it's a natural log, which is okay. The same property applies. Okay, so here it is. Here's the next question we're supposed to be solving. So again, every single term is a logarithm. So I wanted to collect on the left side, so I have one natural log on the left. So if it's an addition, this means a product of x times x plus 3 equaling the natural log of 10. So again, once you get one logarithm equal to one logarithm with the bases the same, you can drop the logarithm and just set the arguments equal. Now this one is not a linear equation. This is going to be easy to solve, but it's not a linear equation. When you multiply x, it's going to be x squared plus 3x equaling 10. So this is a quadratic equation. The minute you have an x squared, it's deemed quadratic. So now I need to set it equal to 0. Anytime it's quadratic, you want to compare it to 0. And once you get it in this position, it should be kind of natural for you to notice that I probably need to factor this thing. So this will factor into an x plus 5 times an x minus 2. If it does not factor, you would go to the quadratic formula. If it does not factor, you would go to the quadratic formula. Then you just set each one of these equal to 0. And in this case, you would get 2 values. Now, I'm not going to square both of these off, and I need to explain why. You have to remember when we were first told something about a logarithm, they said that every logarithm, the base and the argument have to be positive numbers, or it's like undefined. Well, if you take this negative 5 and you put it up here back into this equation, and you replace this x with it, that's going to be the natural log of negative 5 plus 3, which is the natural log of negative 2, which cannot do that, because it says that that argument must be a positive value. So I have to eliminate this one as a solution, but I can keep the 2. So your argument and your base must always be positive. So when you come up with solutions of logarithmic equations, be careful that your result does not make it undefined, meaning making an argument a negative value. All right? So you can see those are not too difficult, so long as you have all log terms. Okay, here's another one typed for me. Here's a logarithm equaling a logarithm plus a logarithm. Every term is a logarithm. So on the right side, I need to combine those. And even on the left side, I need to push this 2 up and make it an exponent so I can then set arguments equal. So the left side will be log base 3 of x squared. And that's a plus sign on the right side, so this is log base 3 of 2 times 3x minus 4. Now I have one logarithm equal to one logarithm. They both have the same base. Remember, you've got to get that coefficient up and out of the way before you can do this. So now I have x squared equaling 2 times 3x minus 4. Once I have an x squared, this is a quadratic. You're thinking a couple of solutions. Check one of them. Make certain it's not negative kind of situation. So this becomes x squared equaling 6x minus 8. I need to set this thing equal to 0 when it's an x squared term, when it's a quadratic equation. So I subtract the 6x and I add the 8 so that it is equal to 0. Now I'm thinking, boy, I hope this thing will factor. But if it doesn't, I will go to the quadratic equation, or the quadratic formula. This one should factor. I believe this factors into an x minus 4 times an x minus 2. Again, it factors, but if you ever get one that doesn't, just go straight to the quadratic formula. I'm going to get two values, a value of 4 and a value of 2. Now, even though they're both positive, you need to look back up at the equation to make sure you're clear. Okay? In the first term, this is just an x. Whoops, this is just an x, so we're good with a positive 4 and a positive 2. With this x, if I have a positive 4, it'd be 12 minus 4, which is positive 8, good. If it's a 2, it's 6 minus 4, which is a positive value. So we're good on both of them. We can claim both of them solutions. And we have it solved. Okay, so the examples we've done, 1 through 5, every term in the equation was a logarithm. And that's how you deal with the logarithmic equations in which every term is a logarithm. Okay, part B, a new title. Logarithmic equations in which not all terms are logarithms. Not all terms are logarithms. So you can see right now in number 1, I have a logarithm on the left which establishes it as a logarithmic equation, but I do not have a logarithm on the right. So here's a logarithmic term. This one is not logarithmic, so I need a new method now. Okay, I don't do the method that we were doing, it's something different. Okay, so in this case, what I'm going to do is I'm going to change it to an exponential equation. So in other words, I'm going to change it, convert it. It would say 5 squared, 5 to the power of 2, will equal the 3x plus 1. So this was a logarithmic equation. I converted it to an exponential equation. Okay, I converted it. And when I converted it, again, it kind of dropped the logarithm. So this is going to say 25 equals 3x plus 1. Now if I subtract 1, 24 will equal 3x. And then when I divide by 3, I get my x value of 8. And if I put it back in to check it to make sure I have a positive argument in my logarithm, that will work. So if not every term is a logarithm, we're going to convert it to an exponential equation. Okay, number 2, I have a logarithm, I don't have a logarithm. All right, so this one I need to convert to an exponential. Well, to convert to an exponential equation, I still need to use those properties to collect the left side into one logarithm. So my left side can be rewritten as log base 3 of a fraction when this is subtraction. So it's x plus 6 over x minus 2. Once I've collected it into one logarithm on the left side or on one side, then I convert it to an exponential equation. So when I do the conversion, it will say 3 squared equals x plus 6 over x minus 2. So here's my conversion to an exponential equation. And once I've done that, I just use my algebraic skills to solve. So this will say 9 equaling x plus 6 over x plus 2. I'm going to cross multiply, so I'm going to put that 9 over 1. So when I cross multiply, it will be 9 times x plus 2 equaling 1 times x plus 6.
I think it's x minus 2.
Oh, what did I do? Oh, it's x minus 2. Okay. I thought it was the minus 6 right there. Okay, thank you. So this is 9x minus 18. This is x plus 6. I like to move my x to the left, so if I subtract x, it would be an 8x minus 18 equaling 6. Then if I add 18 to each side, this would be 24, and then divide by 8, I get a 3. Before I square it off, I should always look back to make certain this is not going to make an argument of a logarithm negative. So an x value of 3 up here, this would be 3 plus 6, which is a positive, 3 minus 2, which is a positive value. So this is a good solution. All right, so in other words, if every term is not a logarithm, I'm going to set myself up to convert it to an exponential equation. The left one was real easy. Number 1 was real easy. Number 2, I did have to collect these two logarithms together to make one logarithmic term so that then I could convert it. All right, here's some more. How did this happen? Did this one not go to the next page either? Okay. Whatever. Okay, so here we go again. Number 3 is log of x plus 15, is that right? Equaling 2 minus log of x. There it is. Okay, so when you have a logarithmic equation, not every term is a logarithm. This 2 is not a logarithmic term. Then the goal is to get the log to one side. Okay, get all your logarithms on one side. Get log terms on one side. Get your logarithmic terms on one side. And I'm going to move them to the left. So I'm going to add log of x to each side of this equation. So it will then be log of x plus 15 plus log of x equals 2. So now we look a whole lot like example 2. So get your logarithms on one side of this equation. Now on the left side I'm adding, so my property says I can make this a product of the x times the x plus 15. And now I'm finally ready to convert it to an exponential equation. Now remember, if there's a common logarithm, it's assuming a base of 10. So this would be 10 squared equaling x times x plus 15. Here's my conversion to an exponential equation. So this becomes 100 equaling x squared plus 15x. And the minute you get an x squared term, you want this thing set equal to 0. The minute you get an x squared term that makes it quadratic, you want to make it equal 0. So this is going to be 0 equaling x squared plus 15x minus 100. Now you say, boy, I hope this thing will factor, because I really don't want to have to go to the quadratic formula. Okay, so 0 equals 20 and 5. We can do this. X plus 20, x minus 5. So I'm going to get x equaling a negative 20 and x equaling 5. Now I'm not going to square these off. Boy, with a negative 20, that's a big negative number. Let me look at my original equation. If I put a negative 20 in here, if I put a negative 20 in right here, automatically it's undefined. Because it has to be a positive argument on a logarithm. So that's for sure that I don't get to have this one. If x is 5, I'm covered in both cases. So x equaling 5 is a good solution, but negative 20 would make my original logarithm have an argument that's negative, which makes it undefined. Okay, so I'm going to try to put the other example right beside it here. So the other example was again to solve, and it is log base 4 of x squared minus 9 minus 3. There's that term that is not a logarithm, equaling log base 4 of x plus 3. And they're very, we couldn't do any of this if the bases were not the same on these logarithms. But the bases, they keep them the same in our equations. All right, so here we are. I have logarithms all over the place. I need the logarithms on the same side of the equation. Okay, I'm going to move my logarithms to the left. So I'm going to subtract log base 4 of x plus 3. So this is going to become log base 4 of x squared minus 9 minus log base 4 of x plus 3 minus 3 equaling 0. I want my logarithms alone. I want that 3 to the other side. I don't want that 3 next to my logarithms. So this will be log base 4 of x squared minus 9 minus log base 4 of x plus 3 equaling a positive 3 when I move the 3 to the right side of this equation. Now we're set up, just as example 3 on the left. We're not quite. We got one more to go, right? One more step to make this before we convert it. Log base 4 of x squared minus 9 over x plus 3 equaling 3. Now we're ready to convert it. We're ready to convert it to an exponential equation. We have one logarithm equal to a number. All right, so 4 cubed equals x squared minus 9 over x plus 3. What is 4 cubed? 64? Mm-hmm. Okay, 64 equals x squared minus 9 over x plus 3. Cross multiply. We're doing quite a bit of cross multiplying. 64 times x plus 3 equals x squared minus 9. $64x plus, okay, what is 3 times 64? Okay, so I have an x squared term. I want to set this thing equal to 0. So I'm going to subtract 64x. And I'm going to subtract 192, right? So what does that become? 201? Is that right? Mm-hmm. What in the world does this turn out to be? Did I do that right? Okay, what goes into 201? 3. Okay, I'm going to pause it while I figure this out. Okay, 3 times 67. So it's going to be a negative 67 and a positive 3. So here we go. X equals 67 and x equals a negative 3. Before I square them off, be really careful. Go back and look at the original equation. Check those arguments of those logarithms to make sure they will be positive if you plug any of these numbers in. The negative 3 is my cautious thought. Okay, so highlighter. If I put a negative 3 right here, that becomes log base 4 of 0, and we cannot do that. 0 is not a positive number. 0 doesn't have a sign. Okay, so you cannot do that. It cannot be 0 either. So the negative 3 doesn't work, and the other one was a big old number. 67. 67 is definitely good. Okay, so we get to have the 67, but we do not get to have the negative 3. Going back, checking to see if they're going to be okay in our logarithms. Okay. Yes, it is. Okay. All right, so applications. What's happening now? If $20,000 is invested in an account earning 2.5% interest compounded continuously, the minute I see this word, you know it's the A equaling P e to the RT. The continuous compounding is that one. Determine how long it will take the money to grow to $45,000. So the question is how many years? How many years will it take it to grow? All right, let me grab my calculator because I'm going to have it. All right, so here we go. They give me the formula, which you should have kind of immediately gone to in your mind anyway, because it's continuous compounding. 2.5% interest will be 0.025. All right, so you start with $20,000 and it grows into $45,000. So your A is 45,000, after time is 45,000, start value is P, 20,000. So this is going to be 45,000 equaling 20,000 e to the 0.025, and the only thing I don't know is T, time, which is what they're asking me. All right, so how do I do this? When you're trying to solve for that exponent, the first thing you want to get rid of is that coefficient of $20,000. So the very first step is to divide off this 20,000. And when you do, these 3 zeros are gone, so it's really 45 over 20. And 45 over 20 is what? 9/4? Correct? Okay, so when you get to this step, this might be where you're a little unsure what to do, but in general, this is always going to be the step, so just kind of learn it now and remember it. At this point, you're going to take the natural log of each side of this equation. So you're going to take the natural log of 9/4 and the natural log of e to the 0.025t. Then you have to remember the natural log of e to the x, or the natural log of e to whatever, is the exponent. The natural log of e to an exponent will equal the exponent. So this right side is 0.025t, and the left side is still a natural log. So to get t, you're going to have the natural log of 9/4 divided by 0.025. So when you do that on your calculator, it'll come up with a number of years. A number of years it takes for $20,000 to more than double. $20,000 to go more than double, up to $45,000. So the natural log of 9/4 divided by 0.025 is going to give you the number of years. And I'm going to round it off. So I come up here with 32.44 years. But I think they said round to the nearest year, so that would be 32 years. That's a long time. But that was a really low interest rate. Really low, right? 2%? That's why it takes so long for it to more than double. So really, this is an excellent, because this is, when you start looking at making investments, your question really is, how long is it going to take this money to grow to be $200,000, okay, or $500,000 if you're talking about retiring? So it's the number of years that's important to you when you make investments for retirement. What is this one? Oh boy, okay. The following formula relates the energy in joules released by an earthquake of magnitude m. So earthquakes use logarithms. When you have an earthquake of magnitude 4, 4 is not a big number, right? But that's because they're using logarithms to make the number smaller, even though it's a huge magnitude. What is the energy released by a magnitude of 6 and a magnitude 7 earthquake? Okay, so your magnitude is your m. So when they say a magnitude of 6, you're supposed to put a 6 in for m. And a magnitude of 7, you're supposed to put a 7 in for m. All right. What in the world do they have to tell me here? As a comparison, a megaton, wow, that sounds big. A megaton nuclear weapon, that's a little bit intimidating, would have an energy release of 4.18 times 10 to the 15th joules at the eruption of a volcano, Krakatoa, y'all heard of that?
Yeah.
In 1883, produced an energy release of 2.09 times 10 to the 19th joules. Wow. Okay, let's play with this. Let's put a magnitude of 6 in. All right, so log of E equals 5.24 plus 1.44 times, let's use a magnitude of 6. Magnitude of 6. All right, so this is log of E, and that's not our baby. That's not our lowercase e. Okay, that's not our little exponential e. That's just e. So this becomes 5.24. Let's go ahead and figure this. 1.44 times 6 plus 5.24 is 13.88. They want me to come up with E. Okay, they want me to find E, the energy. So remember, this is a logarithm, not a natural logarithm, so it has a base of 10. So to solve for E, change it to an exponential function. 10 to the power of 13.88 equals E. Now, what in the world is 10 to the power? This is going to be a big number, right? Okay, Now, if you're looking on your calculator it says 7.58. Oh my goodness, a whole bunch of numbers here. And then there's an E here at 13. What that means is 7.59 times 10 to the 13th power. Correct? That's a big old number, right? That is a huge number. What is that? That's 13. Move that decimal to the right 13 times, right? That'd be 7, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. That many joules. That's a huge amount of energy. When it says up here that a 1 megaton nuclear weapon would have an energy release of 4.18 to the 15th power, this is really close to that number. 10 to the 13th power and 10 to the 15th power. We're up there real close to whatever in the world a 1 megaton nuclear weapon does. That's some pretty serious energy. All right, so let's close this out for learning how to solve logarithmic equations. And yes, the magnitude of an earthquake is based on a logarithmic function, and it is sure releasing a lot of energy.